Would you rather have a bunch of pencils or a bunch of diamonds? Well, maybe I'm easy to please, but I would be OK with either. Even though they look very different and they cost very different amounts, they're both made out of carbon. Carbon can form the graphite that's found in your pencils, and if you squeeze it enough and apply enough pressure, it'll turn into diamond. This is an example of what we would call a phase transition. And the Nobel Prize in Physics a few years ago went to 3 scientists for predicting a very special type of phase transition called a topological phase transition. Now, to a physicist, topological means when the outside, or surface of a material, is different than the inside. So imagine you're holding a chunk of something in your hands, and on the inside, it's an insulator. The electrons are held in place and can't move around very easily. But on the outside, or surface of the material, the electrons are free to move around and conduct electricity like cars on a racetrack. And just like those race cars, they're going a lot faster than normal traffic. Imagine if your silicon-based devices of today could run 100 times faster using these electrons. So even though it's the same material throughout, the outside is different than the inside. And that's what we mean when we say topological. So ever since this prediction, the name of the game has been to find all of the materials we know that display this unique topological property. What most people do is look at complicated combinations of heavy elements on the bottom half of the periodic table. What I did was take a counterintuitive approach and try to find the simplest example of a material that still displays this unique property. So what I did was look at the simplest example of a metal on the periodic table, which is element 3, lithium, and studied that using mathematical models to predict its properties. What I found is that the same way that carbon underwent a phase transition, lithium also undergoes a phase transition. But on top of that, it's a topological phase transition, going from being a normal, arguably boring metal, and as you apply pressure and squeeze it enough, it becomes topological, where the electrons behave differently on the surface than they do on the inside. So this is really exciting, because not only does it give us an entirely new section of the periodic table to look for these materials, but it's also this idea of using pressure as a switch to turn on and off this topological property. And this should inspire us to switch our thinking when designing future devices and technology to harness the potential of these topological materials. Thank you.
What kind of applications do you see?
So one of the most direct applications would be in the realm of microelectronics, and so especially for computing chips, because this is an area where having faster circuitry could really make an improvement, especially since supercomputing power is an increasing demand on global energy consumption, and so this could greatly increase that.
Is this specific for lithium, or could also other atoms be?
It could certainly apply to other elements or combinations of elements, and especially using pressure as a switch.
Thank you very much.